We've built up the tools that we need to solve our next problem, which is the finite two-dimensional disk having uniform charge Q and radius R. The disk lives in the XY plane. Our goal is to, let's just visualize or sketch out the disk from above. We'll place our origin here. So if this disk is living in the XY plane, then the z-axis is, of course, out of the page. We can use x hat, y hat, z hat, or I hat, j hat, k hat, up to you in this situation. Here we want to find the electric field vector as a function of distance z along the z-axis. So you're imagining the z-axis coming out of the page like this. We want to step up the z-axis and determine what's the electric field coming from this disk at each location along that axis. Now, based on our result for the one ring of charge, you have an advantage for solving this problem already. What we'll do is imagine that this disk, this finite two-dimensional disk of radius capital R is built up. You could imagine 3D printing a bunch of these rings. Each has a slightly different radius. If you stacked enough of these rings one on another, you could print out the entire disk. Each ring now, this is where the 3D printer analogy breaks down, each ring has only a differential thickness, dr. Our goal is to determine what's the charge contained in this ring. We will take the result for the electric field from one ring, which we've already solved, and we'll build up our solution using superposition of the electric fields. It's a valid choice. So each ring is going to create a vector field. We know already, fortunately, that those fields can only point in the z direction, right? All of the x and the y components canceled out, as we saw last time. So how much charge is sitting on this infinitesimally thin ring? We'll call that amount of charge dq. When we're working with two-dimensional areas, dq will be the charge per unit area, we call this sigma, times the area of the ring, dA. Right? The sigma for a uniformly charged object spread with charge spread over a surface is just all the charge divided by all the area. In this case, the area of the disk is pi r squared. Knowing this, to determine how much charge is sitting on that ring, we need to know how much area the ring takes up. Imagine slicing it right here and just laying it out flat. I'll exaggerate the shape of it. If its thickness here is dr, the inner circumference of that ring would be 2 pi lowercase r as a variable radius. The outer circumference is going to be 2 pi times this slightly larger radius, which is r plus dr. If you do not know the formula for the area of a trapezoid, it's okay. I don't know it either. I'm going to take the area of this rectangle first and add the area of the two small triangles at the end. So the total amount of area here, dA, will be the rectangle, 2 pi r dr area, and we're going to add two triangle areas, and I can remember that the area of a triangle is a half the base times the height. Our base here is pi dr, and the height of the triangles is dr. So you end up with an expression, 2 pi r dr plus pi times dr squared, and then you say, well, dr is the smallest length imaginable. Now I'm going to square it. Well, it's definitely something that you should be ignoring at that point. So we'll throw out this term entirely. It's unimaginably smaller than this term. We will use the result then that the area of each ring is its inner circumference, 2 pi r, times its thickness, dr. That is an important result that we'll be using throughout the semester. So make note of the dA for a ring. All right. The amount of charge then is our sigma, we said was q over pi big R squared, times the dA, 2 pi r dr. So this can simplify a bit. We have 2q variable lowercase r over the capital R radius of the disk squared dr. Now, here is the key. We're going to reduce, reuse, recycle the ring of charge result, the one ring of charge. Each of these dq rings will create electric field of magnitude dE, right? And I'll just write out the result. You may look back in your notes. It's k dq. Now we have to replace the charge on that ring with the charge on this ring, which is a smaller dq. Had a z in the numerator, divide by z squared plus now the variable radius squared to the 3/2 power. Now, using the power of the calculus, the total electric field magnitude will just be the vector sum of all of these little dE magnitudes. So we have a bunch of constants that I'll pull out front, which do not participate in the integral we care about, which is we're adding up all of the different rings of lowercase radius r. So we'll be integrating over lowercase r. The bounds of this integral should be 0 at the origin to capital R at the edge of the disk. We have r over z squared plus r squared to the 3 halves. And you can tackle this with a simple u substitution, r squared plus z squared, then your du would end up being 2r dr. The electric field is kqz over capital R squared. We have to change our limits of integration since we changed our variable to u. We have du over u to the 3 halves. This is kqz over big R squared minus 2 u to the minus 1 half with limits. Minus 2k qz over r squared 1 over root big R squared plus z squared minus 1 over absolute value z. Because you're taking the square root of z squared, don't lose that absolute value. For now, we'll just deal with positive values of z above the xy plane. And we'll say that our E field vector is a vector pointing in the plus k hat direction up the z-axis, 2kq over big R squared, quantity 1 minus z times z squared plus big R squared to the minus 1 half. I want you to always think about the limits of your results. Reasonable limit here in the case that you are much farther away from the disk than its radius, it should look like a point charge, does it? You have E approaching 2kq over big R squared. You have to break out your binomial expansion. 1 minus 1, 1 plus power, which is negative a half, r squared over z squared. And that is, in fact, kq over z squared, just like a point charge. Now the other limit, which I want you to consider and we'll deal with in class, leads you into page 39 in the activities manual, where we'll find that this two-dimensional result of the disk will build out as you let the radius go to infinity. We'll build out an infinite plane of charge, and we'll find a surprising result for that electric field. Stay tuned.